we present RackLay, a deep neural network for monocular multi-layer layout prediction for warehouses. Given an image of a warehouse rack, RackLay predicts the top view and front view layouts for rack shelves in a shelf-centric or egocentric frame depending on the use case. The two kinds of layouts, egocentric and shelf-centric, are depicted here. Shelf-centric layouts are agnostic to the movement of the camera and are fixed to the center of the layout frame. Egocentric layouts shift within the layout with respect to the camera, shown as a gray icon. This enables us to infer the position of the rack with respect to the camera. Using the shelf-centric layouts, we get layouts centered around the rack. RackLay can predict the layouts for different rack occupancies. As the geometry of the rack changes, the corresponding layouts also update accordingly. This enables us to accurately reconstruct the rack and calculate free space. Using egocentric layouts, we can get the position of the rack with respect to the camera. We can use these layouts for downstream tasks such as generating an SDF. Here, observe how as the camera moves, we are able to accurately predict the position of the rack and thus integrate the SDF for each new viewpoint with minimal noise. The camera trajectory too gets estimated accurately, purely from the layouts without resorting to any kind of descriptors, thereby vindicating the efficacy and accuracy of the layout estimation pipeline. This is the architecture diagram for RackLay. It comprises a context encoder, followed by a top view and front view decoder that predicts multi-channel outputs, which are passed to the discriminator for refinement. Here, we display the diversity of our domain randomized dataset. Observe how the color and texture of the boxes, racks, floors and walls are random. The size of the boxes and the height to which they are stacked are also randomized. The density of box placement varies from sparse to dense. The background is either a wall or a busy warehouse with racks in the background. Here, we present the predictions and 3D reconstructions of RackLay on varying images. As shown, RackLay can predict the layouts for the domain randomization described earlier. Our domain randomized data enables Sim2Real transfer. Here, we present the predictions of our network on real-world images from two different datasets. These datasets contain different boxes, rack types, colors, textures and lighting conditions. We can see that the results are at par with the results on synthetic data. The domain randomization described earlier enables Sim2Real transfer to real-world images. Here, we show a comparison of point RCNN with our network outputs, only for the bottom shelf. Since point RCNN is designed assuming the presence of a single dominant ground plane, it fails to predict boxes on all levels. Thus, point RCNN can detect objects on a single plane only, unlike RackLay that estimates multi-layer layouts. We can see that point RCNN fails to predict the position and rotation of the boxes accurately. In some cases, it also fails to predict the presence of a box. We also release WareSynth, a synthetic data generation pipeline that generates randomized 3D warehouse scenes customizable by the user, automates the process of data capture and generates desired corresponding annotations. WareSynth is capable of exporting to various popular annotation formats and can be used for applications being developed in warehouse settings. It provisions for extensive variation and domain randomization in the generated data, which enables Sim2Real transfer. We will make all code and data publicly available. Thank you.